Good morning, everyone. Dan and moderators, thanks for the opportunity to be here speaking about this interesting and exciting topic. I didn't know it was an NCME, so those are my disclosures.
Okay.
All right, perfect. So let's talk. So artificial intelligence is getting a lot of attention in the media, especially in the healthcare, but it's not something that's any new to us. It's almost 70 years old. But was only since recently when all the processing power and GPUs and the computers and the big data came about that people are talking more about artificial intelligence. And there is always this fear if like a robot's going to be taking our jobs. Well, we're going to be trying to talk about that a little bit. If that ever happens, people always talk about something called the universal income, that the government is going to be paying us just to be, residents in the countries, and then we have somebody or robots who can play while the other ones work for us. So what is artificial intelligence? So AI is defined as the study of the algorithms that actually give machines the ability to reason and perform cognitive functions like we do, like problem solving, object and word recognition, and sometimes even infer world states and make decisions. So why is this important to us? If you look at this, all the investments, and you see the healthcare, do I have a laser here? Right on the top is like now leading all the investments on artificial intelligence. Not just that, the prediction going from emerging to being implicit, about 2022, healthcare services will be highly, invested with new applications of artificial intelligence. So even the Pentagon is already investing $2 billion, and the president said there's going to be one of the priorities of his government to invest in artificial intelligence. And Nature just launched like a new magazine only on AI and machine learning. And when people ask, so how does that play for us surgeons? If you look right there in the middle of the graph, it shows when the researchers believe that some fields will be replaced by machine learning, AI, and sometimes automation. And the prediction for surgeons is about within 30 years going to have a massive, change in our workflow. So, like Industrial Revolution, the question is, are we doing like a man versus machine? And are the machines going to be actually taking our jobs and doing what we do? Clearly, we can see that a lot of automation tasks in our industry can actually be taken very sharply by machines, and even like the samurai competition of the sword. So, but different than the Industrial Revolution, that they actually integrate machines to the workflow, was mainly for the mechanization of it. Now we're actually living in the cognitive revolution, where AI has the potential to position machines not only to outperform us, but to outthink us. But at the same time, what we should do is, with this shift in the workflow, we should make us more productive. So examples are AlphaGo, which already is a champion in the world on the game Go, won against the current champion. And it was like a algorithm that was trained called like adversarial neural networks. An example in our lives, IBM Watson and Tesla Autopilot. And so why all of this is important to cars and Watson and computers? Because this eventually going to come to the healthcare. You're already seeing like through natural language processing and through other methods. But more importantly, you're going to be focused at the end of this talk on computer vision. That's very important for surgeons and endoscopies. So I'm just going to go very briefly about the four major subfields. So machine learning. So traditional computing, what it does is requires assumptions of linear relationships, yes or no, 0 and 1s. What machine learning does is enable machines to make predictions, learn on recognizing patterns. And there are two different ways to do this, mainly. One is called supervised learning. The other one's unsupervised learning. Of course, supervised learning, you train the machines to recognize patterns, versus unsupervised learning, the machines just run free and try to pick and aggregate what's common. An example here, on the left, you have a supervised learning where we are feeding images of gallbladders as our training set and training the machine. And then when we give images of a gallbladder and there was like a gastric specimen, the computer just spit out, say, this is gallbladder, this is not gallbladder. So it doesn't know what it is because it wasn't labeled. On the other side, when you see the unsupervised learning, what happened is you just feed large amounts of information and the computer groups all of them. Group all the gallbladders together, and now the difference, we're still a gallbladder, but there was a bleeding. So Examples, you can use machine learning in cancer prediction prognosis. There was already this very nice study where they, just by looking about the, on claims data and on the CPT codes, the machine was able to predict what's going to be the outcome on those patients with lung cancer. And there is another examples in medicine as well. The other thing that is permeating our lives already is natural language processing. We use that like when we talk to our phones or to dictate or for the phone to read something back to us. Natural language process is the way that computers understand our language. So a lot of EMRs right now, our hospital, we use Epic, and our dictations after we've done that, or either if you dictate them or just type them in, natural language processing is going to search all the keywords and going to make a recommendation for billing. Those are examples: post-operative complications detection, advanced averts, and assistive medical records. So what is an artificial neural network? So an artificial neural network, it came actually from a perceptron. A perceptron was a very basic unit, it's a binary. That was the old phones used to have old computers. But the difference is that on artificial neural network, they try to mirror this on the neurons, where you have several different input layers. I'm sorry, one input layer with several different, like quote-unquote synapses. Go to the node, and the node has a function and an activation function, and then gives you an output result. In other words, what it means is, if you're giving words or pictures, it goes to the function recognizes them yes or no, and say what it was on the output. One advantage about the neural networks is, if something is wrong, if you look at the image on the right side, let's see if the laser is working. Yeah. On the image on the right side, what happened is, let's say if I gave an image of a cat, went through the neural network, and it was identified incorrectly, I can tell the machine that it was wrong, and it will back propagate, and we're going to deactivate those nodes that make that prediction. So the next time that image goes through it, it will be correct. So this is an example about a deep neural network. And what is a deep neural network? It only means several layers stacked together. So that's why they gave the name. When they talk about convolutional neural networks, is another different type of it, for mainly to see images through activation maps. The largest deep neural network we have right now is about 10 billion connections, but the human brain still has 1 trillion to 1 quadrillion synapses. So this is an example about training neural network, right? This is from Google DeepMind, and the algorithm was pretty much set to tell the machine that doesn't know it's a game, have no idea what does it mean, but it's like, if you score a point, that's a reward. If you die or if you don't score points, and then that's going to be something negative. And as it goes, the machine wasn't trained to use the pedal. The machine wasn't trained to recognize the patterns within the game. It was just like dying and not scoring points, and it was getting all the negative rewards. So all the back propagation was occurring, and the machine was being reprogrammed. So this was after 120 minutes of training. And again, machine has no idea about the rules of the game. And if you take a step further, and you train the machine even further, you're going to see the outstanding results. This is with 240 minutes of training. Even find a way to trick the game and drill a hole on the left corner, and then gets the ball inside, and look at that. And this is a simple command, you know, you score a point, positive, you die is negative, so. Now, let's get to computer vision. Computer vision is probably going to be the most important of all the features that artificial intelligence has on its helm, because it's core for what we do. We deal with vision all the time: laparoscopy, endoscopy, robotic surgery. The way machine sees is by pixels and 3 numbers and the RBG. When you get that portion of those pixels, they become a bunch of numbers, and it becomes probability, goes through all those functions and come out. They try to reconstruct that and come up with an image or with a classifier. For example, that image classification, when it was trained, was 82% to be a cat, but 15% could be a dog, and 2 a hat, and 1 a mug. When we talk about the convolutional neural networks that I mentioned before, If you look at, in 2010, there was this competition called ImageNet, where they have like a CFAR 10. They give like 10 classifiers: dogs, cats, birds, planes, cars. And the goal is that for all those images to go through the network and be considered to be accurate. In 2010, it was about 25% error. In 2015, it's less than 5% error. So that led to things such as Facebook recognition. And why can't we then start applying this to surgery? And we should, right? So another thing that's core about computer vision is all about the annotation. Video annotation is very important. If you do a bad annotation, the machine going to make bad results about predictions. So in a healthcare, what we already have is computer-aided diagnosis, image-guided surgery, and virtual colonoscopy. This was a very elegant study done at Stanford, where they were looking about to try to identify, just based on image, skin pathologies. And what they did was a very large data set, 2,000 different diseases, and then they tested that. Of course, they label all that data, so we're very well annotated. And when they tested against a board-certified dermatologist, it was a part of the diagnosis. So that's is a great application of like how computer vision can be used for surgery, in medicine. The other example is just an old video, but it's already enhancing polyp detection. As the image goes through the colonoscopy, it tags polyp, 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 polyp. I mean, cannot tell which type of polyp it is at the moment, but I know many companies are already working on systems similar to this. And on computer vision, for surgery, every time you see one frame, one image, there's like thousands of the information that is there that we sometimes our like a naked eye cannot even perceive that. So imagine when you can actually then apply this for segmenting surgical procedures in real time, right? This is one of the studies we did at MGH where we were training the machine on how to do real-time segmentation of sleeve gastrectomies. Okay, spread that a little bit. So here what we did was we did a training set, test set, trained the machine about those are the phases of the operation. Then we gave new videos to the machine, and then we rated what the machine rated with expert surgeons. And that yielded 92% accuracy on real-time identification of this type of procedure. The other thing we did was, as we are doing the procedure, the machine was coming out the probability log of what step is the one that's occurring in making the prediction of what's going to be the next step. For example, just for the sake of time, I'm going to expedite this and go to what we generated, what we call the surgical fingerprints. So each surgery will have its own surgical fingerprint that's going to be related to the surgeon and the procedure. If those fingerprints are correct, very likely this procedure was done in a correct fashion. However, imagine like when a surgical fingerprint or a procedure was done in a different manner, may trigger a review or may trigger a concern. So in this case, this was a absolutely normal case, a normal surgical fingerprint is being generated. Now as is being stapling, bagging, and then removed. On a case 2, right, however, this machine was not trained to recognize adhesions and lines of adhesions. So it gets quite confused about making the prediction. Is that the liver, not the liver? Is that the gastrocolic ligament or not? And in the end, it generates an abnormal surgical fingerprint, if you can compare that. So that's one of the other applications we can already have that. Where we can use this for attending the notification system if you're a fellow or if your resident's kind of deviating from standards, for telementoring to establish automated communication of that surgeon that less experience to other surgeons who can actually guide them through the procedure, and even perhaps for peer review, like for credentialing or recredentialing. And what I want to bring to this is like the future of clinical decision making is once we can actually train the machine with all our knowledge from all the surgeons at the same time, the machine learns exponentially. And what we can create is this, what we call the collective surgical consciousness. And imagine like if you're going through a case that's absolutely normal, the machine said, this is normal, keep going. But then suddenly like you're deviating from the standard, and then you cut common bile duct, and you don't even notice. But then the machine's already trained, and we're able to real time to warn you, you should be able to stop, or perhaps just call for help through telementoring. So I'm not going to talk much about automation. It's not much what's happening right now. We're really far away from it. Although I was at the Financial Times Summit in Digital Surgery 2 weeks ago, and people from UC Berkeley are presenting very elegant studies about showing the Da Vinci cutting through FLS tasks, What we know about automation at the moment, a Star robot was able to suture as fast as surgeons, but it was quite special circumstances. And what I want to bring is, when we get all the synergy with like a natural language processing, machine learning, neural networks, computer vision, we can try to replicate in medicine what's happening on the car industry. This is how the Tesla Autopilot sees the road, right? All those blocks identify, and imagine that as you're driving or as you're doing the surgery, say, this is the common bile duct, this is a vessel, be careful, that might be cancer, you should call for help, you should consider other approaches. Are we far from this? At the moment, yes. But if we do this in a proactive manner, and we all be involved on creating this collective surgical consciousness, I think we can always get there in the next several years. We already showed that volume matters and centers of excellence matters. If we can actually bring this to all the surgeons in rural areas and the military and less experienced surgeons, that would be a game changer. So I will just conclude here because I don't have much time. This is showing like the continuation of that test. You have to do 1,000 cuts. And what happens is the samurai, in the beginning, thinks going to win it, but samurai gets tired, gets frustrated, the machine keeps going, right? And imagine if this is our lives as surgeons and physicians that we're not proactive on creating this right now. Maybe the industry is going to be dictating what we do. Nothing wrong with that as long as we are part of it, as part of we're helping to create this future. So we shouldn't be fighting the machines. We shouldn't be scared about artificial intelligence. We should be cooperating then to make us an augmented intelligence. And I'll end right here. Thank you.